Alright, welcome back to another AP video. Of course, not sponsored by College Board, of me just doing another AP Physics 1 FRQ. And this time, it seems like we're met with an FRQ that's about rotating systems. So my mind will be thinking about something about either circular motion or rotational motion. But since we're given this cool little diagram here, I could probably tell it's more about rotational motion than centripetal acceleration or anything like that. Okay, so the first thing we want to do, of course, in these type of questions is to look at questions we could get free marks on. So question A seems to be pretty standard. It's what you would expect for your first question. Question B seems to be a bit more mathematical. And sometimes when it feels like you can't do part A first, probably you would do part B first because it doesn't seem to rely on part A, but part A would definitely help you formulate your response for part B. Now, Part C feels like a bit more difficult because it appears that it relies on what you did in Part A because the two grids appear again. Part D is kind of what you interpret from Part A. So we're probably going to have to do this problem once again in chronological order. Okay, so let's start from the very start. We are supposed to draw a angular velocity with respect to time graph and an angular acceleration with respect to time graph for the disk. And we know that there is a constant torque exerted on the disk. So that means that there's going to be a constant angular acceleration that opposes the angular velocity. And we're given that the disk eventually comes to rest at time t equals to t1. So right at this point here. So that means that if it starts at omega naught, which it does as it gives live a problem, since the angular acceleration is for no means it has to be linear, we're going to expect that the graph for the angular velocity with respect to time, it should also be linear. Now, on the AP exam, hopefully you'd have a ruler, so you'd actually use a ruler. But I'm a bit lazy here, so I'm not using the ruler. But definitely do use any sharp edge that you might have. Okay, now for part two, we know that the angular acceleration is negative because it's in the opposite direction of the angular velocity as defined by the problem. So we probably want to have a negative angular acceleration. Now we are lucky in the aspect that we don't actually have to deal with the relative scales of the problem. So all we really need to do is draw a straight line right across here, and we could call it a day. Normally, some other problems might actually ask you to label what this value might be, but to just play it safe, since we know that the slope is 2 and 1 across, we'll probably have a angular acceleration of -2 units. Okay, so that was part A. That wasn't too bad. Now, part B is asking us to find the frictional torque exerted on the disk uh, is T naught. Sorry, so it's actually asking us to derive an equation for the rotational inertia of a disk. Well, when I think about this, the first thing I'm thinking is, well, I have to express somehow rotational inertia with torque. Now we know that torque is the cross product between the lever arm and the force exerted on the system, but we're not quite given the radius of a disk nor the force exerted on it, so that'll be actually kind of useless. So we have to go about this in another way. And luckily, we still have this equation that T naught is our T net in this case, because the frictional torque is our only torque present, is also equal to the rotational inertia multiplied by the net angular acceleration. So all we really need to do now is find what is alpha net. Well, to do this, we could probably use our kinematic equations, but in a rotational sense. So we have omega I, omega F, alpha, which is what we're trying to find. We have our change in angular displacement, which we do not have, and we have change in time. And we realize that change in time is simply t1 minus 0. That is simply t1. We know that the disk comes to a stop, so Vf and omega f is 0. And we know that the disk, as given by the problem, has an initial velocity of omega naught. Okay, so this is making us think we don't want to have a equation with delta alpha delta theta, so that would be probably something like omega f is equal to omega I plus alpha t. All right. And then now, since we're only really dealing with magnitudes, they gave us a magnitude here. We won't care about the signage or anything. All we really need to do is find the absolute value of the angular acceleration. And we know that omega I is 0. So that simply means that's just omega f divided by our delta t. And that is simply omega f over t1. Okay, well that was relatively simple, and hopefully this answer makes sense. All we really need to do now is plug this expression into this expression. So what we should get after isolating for I is that I is equal to tau naught multiplied by t1 over omega f. You might want to show a bit more work on this, but honestly, it's fine if you jump straight to the conclusion with this. All right, so that is our answer for B. Now in part C, we note that the setup is the same, but now at time t equals to 1/2 t1. So right over here, the student starts dripping oil on the contact surface between the axles. So that's right over here. So that's going to decrease the frictional torque that's being exerted on the system. And as time passes, more and more oil reaches that contact surface. So probably the retarding acceleration will decrease with respect to time then. Okay, now that we have that set up, let's actually try to complete this problem. So we'll have something like this. And now I take back my words of being lazy. I won't be lazy for this problem anymore. At the start, the angular velocity will decrease just like it once did, all the way until 1/2 ti. And it is the same thing for the angular acceleration. There is no difference at all. These two parts are the same. Now, the interesting part comes after 1/2 ti. We know that the angular acceleration will decrease, well, the magnitude will decrease because the frictional torque is decreasing due to the oil, which is making the contact more smoother and less rough. So the angular acceleration will probably decrease. And luckily for this problem, we don't need to determine if that decrease is going to be exponential, logarithmic, quadratic, linear. I'm just going to guess that it's probably exponential, just based on the questions that I've done before. So if this is an exponential decrease with an asymptote of 0, well, it'll probably be close to the same thing here. The angular velocity will still decrease. It's not going to increase for any reason. It will decrease, and it will also approach 0, but it won't hit quite 0 yet. So we'll do something like this, because the friction will eventually die off, and there will be an asymptote that's hit. All right, so that's our graphs for CI and CII. In part D, we're asked to interpret if these two equations make sense or not. So we're given two equations, and we really have to see, well, which equation better mathematically models this experiment. So first of all, whenever you meet these type of questions, you should think, well, what happens when a certain value approaches infinity or 0? Okay, so that's probably an approach that we should take in this problem. So let's look at equation 1 over here. For equation 1, as t approaches to infinity, we note that tau will also approach infinity. Well, that doesn't quite make sense. There's no reason for the frictional torque to approach infinity. So I don't think equation 1 really makes that much sense. So we're going to put 1 on the no list for now, and let's look at equation 2. For equation 2, as t approaches to infinity, the denominator will become very large, and c2 is simply a constant, which is much less than infinity, so this tau will actually approach 0. And that makes sense, because as given by our model here, our angular acceleration is going to approach to 0. And even if it was a linear decrease, it would be approaching 0 and it stop at 0. So really model 2 makes sense here. So we will go with equation 2. Now don't forget to briefly explain why. So what we really need to do here is quite simple. We say in equation 2, as time approaches, we could say infinity, or we could simply say a large value, the net torque will approach 0. Well, let's say will converge to 0. Okay? Well, if that's the case, then, well, all we really need to do is now also explain why the other equation is not plausible. But first of all, we have to actually explain why this makes sense. This makes sense since the friction is decreasing to 0 as more and more drippy oil is added between the axle. However, in equation 1, as time approaches a large value, the net torque blows up into infinity. Or we should say, blows up unchecked or unbounded. A really large value. This does not make any sense, as there is no reason for the torque to be infinitely strong, as even if it were, we would expect the system to have an angular velocity of 0 in the end. All right. Now, probably if this was on the AP exam, I would probably delete this because there's no need to have a concession argument here. So I would probably delete this and just keep this. This is good enough. So now that we have all of this, we should be good to pause and enjoy how this problem wasn't actually that bad. And while some problems look really intimidating at the start, if you sit down and just go through the problem, you'll be all right. Okay, well, that does it for this second video. I hope to catch you on the next one, and I'll see you again soon.